Anyway, so we're finally doing fiction again. I finally said what a conservative force is, even though we actually did talk about a little bit in the math section. And I love One Piece. That's another thing I will say. Um, why am I saying that? I have no idea. Hmm. Can I go back to the physics section? As you can see, because of how big this is, it's becoming a pain in the ass. I can't wait for it to be done. Right now, it's 601 pages, which means I have to delete another section, um, and move it to book number two, probably Chemistry 6A. That section is going to be removed and put into the second book. It's going to continuously happen until this book is finished. I want this to actually be 580 pages because the 20 pages give me margin of room for me to actually add more questions because there's parts here that I want to add more questions to. And slowly and maturely, even Physics 2C might be in book number two. That's kind of the idea my brain is saying I should probably do that, seeing how big this is turning out to be. I forgot to do the arc length question, like that one. That one I definitely want to do in projectile motion. Like I want to do like get the arc length for 5 seconds, like up to here, like 1, 2, 3, 4, 5. Get the arc length of that, which is totally possible. What you have to do is you have to get the dt. There's two ways. Keep it in a xdt form, so you know how arc length is getting the derivative of dx dt parentheses square plus dy dt and parentheses square to the square root, and then do the integral. You could do that with the product thing and make a polynomial and do power rule continuously and expand all of it. I would expand it because that's easier probably than doing all the use up. It depends actually, but that's kind of the. I don't know how useful that is. Probably never useful. But is it a dang hard question? Yeah, and it doesn't tick all the boxes for. Does it show you the integral? And yeah, does it show that you know the difference between displacement and distance? Yeah, I don't see why not. You can make that question. It's a bad question, totally in a test situation because it doesn't test you, but as a homework question, it would be okay. It would be a retarded question, in my opinion, and I would question the professor's sanity if they ever gave me that question because there's no point to it later on. Actually, that means it's a bad question, so maybe I shouldn't do that question. Okay, you're right. There's a reason that no one actually puts that question out. It's because it's bad. A lot. My brain is starting to think of what questions are horrible, that's why I deleted so much of the prehistoric questions from a long time ago. A lot of them are deleted for one reason for another. All right, we're starting to do friction finally, and I realized that we need to go to basic 101 with friction. One thing I hate about friction is that they make it seem like there's a how do I put it? There, I love friction, okay, but there's something a misconception that a lot of people have. When you have a frictional force like this, when you start off FFR, over here I put one person because this is the most confusing part of all of friction. Friction is a reaction force, so the same as normal force. So the gravitational means everything for it, which maybe I should explain more. But you need another force. This is a force applied. Maybe I should write something to make it more clear. But then again, this in a lecture setting, this can be copy and paste really well. And I think they would like it. I purposely chose pink because it's interesting. I like pink. I was looking at all the colors and saying what color would be most interesting. I was gonna go for this color. It looked like a white human, or maybe we go for orange like Donald Trump as a funny joke, or red, but all of them were brown or something like this. And I was like, yeah, I mean, that sounds racist. So I'm going to just choose pink because I don't want to be called a racist. Anyway, um, Does that make you a racist now? I'm just thinking that might be hypocritical thinking about it. Uh, uh, because uh, into trying to not be racist, I kind of proved my point that I'm racist, and uh, I didn't think of that. Maybe I should have just chosen white as the default thing, or maybe I should have chose the default skin like this, and then not pink. I don't know now. Let's just leave it pink for now. I might decide not to do that. Anyway, what's happening is that when there's a force like this, when there's not enough force, you see how there's different levels of force I can put this on, but even then, it's still staying the same place. This is not the same force I'm putting on it. I wish there's a better visual, but this is the visual I made up. So, and I actually don't like it a little bit. A bit. This doesn't look the same size as this. So let me. Yeah, that looks like the same size, and I like it over here instead. Yeah, that's the same size. Let me put it over here near the center of mass. Okay. What the? Let me just decrease the size. I didn't expect that to happen. I know why that happened because of this one. Anyway, UK is kinetic friction, which as you can see is a different coefficient you have to measure afterwards. The friction from a static friction and the kinetic friction is different. Where usually, most cases, kinetic friction coefficient is less than the static one because of the moment. I imagine this. You know how if something is in motion, it's easier to move it. That's what I personally think of friction. So it's easier to move something that's already in motion, and it's not really second first Newton's first law, but my brain goes to that. You know how the Newton's first law said an object in motion will stay in motion. I thought it was inertial frame for the longest time. Stay in motion unless acted upon by another shenanigans. So if this goes like, if you need another force to make it go another direction. So that's what I think about kinetic friction a little bit. I used to think it was something like inertial frame. Very why I thought that was in physics 2A. I was taught that you know. Uh, an object in motion stays in motion, that's shenanigans. But in physics 4A, I learned that inertial frame is the only important part of Newton's first law, and I forgot the first part. So I only remembered inertial frame, and then I went to MAE 30A, which was dynamics later on, and I was asking in office hours why this happened, the first Newton's first law, and he was saying, no, Newton's first law is a object will stay in motion unless acted upon by another force. And I was saying that's wrong, it's inertial frame. And obviously I'm wrong because Google's right and I'm stupid. Yeah, that was embarrassing. Anyway, but embarrassing questions are embarrassing. Anyways, yeah, so here is what we have here. Uh, I I think it explains pretty well what's going on. Um, Although I wouldn't, don't do this. Don't push on someone. It's not the best way to move 100 kilogram boulder. You it's better to go parallel with each other because your body is not gonna like it because you're not a really you know your force is transferred to here doesn't really work really that well. Probably hurt you more than anything else if you do it that way. Anyway, that's the idea. I'm gonna do now. I really haven't done much with conservative because we're gonna actually revisit this in energy because I personally believe that energy is the easier way to think of conservative versus uh, non-conservative forces because uh, you can think of friction as there's energy lost. Yeah, And the thing about I didn't like about physics class is that they say gravity is conserved, uh, but it always confused me the way they explained it. Let me tell you that gravity is conserved by going down like this, right? It's conserved because the energy is consistent from here to over here. But that's only true if the velocity is still here. So it's if this is I never liked the idea of this conversation. So if this is over here and the professor said that is conserved, I don't really. I mean, it's true, it's correct, but I never really liked it because the reasoning is that if you move it all back, it's the same potential energy. But that's true. But um, the velocity is counted into that. So what I'm trying to say is that what you should be thinking of, what you should. Let me see if this is actually in video. Uh, is this shown? Yes, this is. Uh, okay. So what you should be thinking of, in my personal opinion, is like this. So in this space over here, not when it hits the ground. Let's just never say it hits the ground. Oh shit. Let's not ignore that. Uh, so if um if it stays over here and it starts at zero velocity and it ends at like 10 velocity or something, because 10 meters per second, which means uh, I'm not going to calculate that. That was a pain in the ass. So over here, somewhere over here is 10 meters per second, and that is why I conserve. So if that energy is the same as this energy on the top, and that's what it really means. So in reality, it takes that much force to go up. Energy lost, not lost, converted into kinetic energy. So why I don't like about when this is flat on the uh, ground floor is that the energy is already dissipated. That always confused me. I never liked that. So um, that's why I like that explanation in the air more than the explanation where it hits the ground, because the energy is dissipated to the atmosphere with sound, or in this case, normal force. The part of it is sound because you hear the sound. The other case is the normal force from the books over here. Oh, by the way, this book is pretty good. I haven't really finished it. But, um, that's the reasoning I like to have. And I'm out of bread already, which means I'm fucking